Hello everyone. Hi Poonam, Ajit, Ashish.
Yes, sir.
Okay, great. So I hope you are following the lectures. You watch the week 7 content. So you are enjoying course or not? Ashish, are you there, Ajit? Okay, let's begin our today's session. So my slides are visible. Hello. Okay. So good evening, everyone. I'm Karthik Jadhav, PMRF Research Scholar in the Department of WRDM IT Roorkee. And I welcome you all in the problem solving session of week 7 of the course Micro Irrigation Engineering. The course is run by NPTL, and this content is created by Professor K.N. Tiwari of IT Kharagpur. So if you have any queries related to this problem solving session we have conducted till now, you can write directly to this given email ID, or you can also write in the course forum. So let's quickly recap our course, what we have covered till now, past 6 weeks. So we have completed almost half of the course. And so in this course, we have started with the introduction and scope of irrigation, and we understand that why micro irrigation is important, and we have also understand that how we can compute the crop water requirement using various equations and agrometeorological instruments. Next to that, we have understand that we have the very limited water resources in this globe. We started the irrigation water management, like starting from how we can monitor irrigation water and how we can properly schedule, right? And next to that, once we have the water at our field, or we identified the source of water nearby our farm, either surface water or groundwater, we learned about how we can lift that water to our field using various water lifts and pumps. And we also need to make sure about the irrigation water quality, because bad quality of water is not suitable for crops, and that directly related to the crop yield. And week 4, we have also seen irrigation methods, various traditional irrigation method as well as the advanced and modern irrigation methods like micro irrigation system, that is subsurface irrigation, subsurface micro irrigation system, surface micro irrigation system. And in week 5, we have particularly focused on the drip irrigation system, its type and design consideration. And in drip irrigation system, we have found that we can also apply the fertigation, which is fundamental requirement by any crop. So, previous week, we have discussed about various problems related to the fertigation and its application methods, particularly dealing with the drip irrigation system. We have also seen various kind of filtration system that are required by drip irrigation system, because uh, irrigation water quality we are using, that may contain various kind of physical, biological as well as chemical contaminants. So that may cause the clogging of the drip irrigation system, because this system involves very small diameter component, right? So in today's session, we will discuss about the various questions related to the installation, operation, and maintenance of drip irrigation system. Then we have also will also focus on the drip irrigation components, and lastly, the soil water movement during drip through drip emitter, because we know that in drip irrigation we are generally providing water with very slow rate and with a very high frequency as compared to surface irrigation methods. So soil water movement during this kind of system, micro irrigation system, is totally different as related to the traditional irrigation water system. So let's quickly recap. Let's summarize the week 6 content. So we have started with the examples on the design of drip irrigation system. In that, as you mentioned, that the first fundamental requirement is the water, both crops and field unit, right? So once we have identified what is the crop water requirement based on the crop type and type of soils we have, next to that we need to decide the emitter selection based on the water requirement, daily water requirement to that particular plant, and that irrigation selection in terms of that is either point source, non-point source, or also the discharge of that emitter, what kind of discharge we require from that emitter. So once we have that emitter, then we'll focus on discharge through each lateral. Then lateral is connected with submain line and submain is connected with main line. So we'll deal with all this. We already saw, right? And we have also seen that filter selection based on the irrigation water quality, right? So in next lecture, we have started introduction of fertigation system. We understand the difference between fertilization and fertigation, then history of fertigation. Also, the major type of fertilizer we are generally applying through drip irrigation system, that is nitrogen, potash, and phosphorus and potash. So next to that, various type of methods we have also seen, that is fertigation application method, that is Venturi injector, fertilizer tank, and injection system, right? And we have also compared advantages and disadvantages of each system. Basically, we compared each fertigation methods, and in that lecture we have also covered the fertigation system design, right? So this is the Venturi injector system, right? This is injection system, pressure injection system. Okay? In this we are then using piston movement, right? Based on piston movement, the pressure is created that draw the fertilizer we have prepared. So in continue with the comparison of fertigation methods, we have found that we have totally we have learned about 3 fertigation systems. One is the bypass tank, second is the Venturi injector, we have seen that figure in last slide, and third is fertilizer pumps. So among all these, in summary, we can say that bypass tank is simple in construction and hence it is available at low cost, but it offers limited control over concentration and automation. So we cannot control here the flow rate and the concentration of fertilizer we are trying to apply. While Venturi injector is a middle ground option. Okay, so it have a balanced cost, also relatively complex compared to the bypass tank, and has a high head loss. But the major problem in this Venturi injector is they have a higher head loss. And in fertilizer pump, this is the most advanced and automated system, and it provides high control and efficiency, but the cost of this kind of system is very high. So in next lecture of week 6, we have designed the fertigation system, right? And again, this also we need to have the fundamental, like what is the fertilizer requirement by that particular soil and crops, and at what crop growth stage, right? Based on that, we have calculated all these components, and finally we have the fertilizer tank capacity that we need to require during entire crop duration. In final lecture of week 6, we have discussed various types of filters and the problems that uh, may generate the issues like clogging in drip emitter, right? If we have not applied proper filtration system. So let's now move on to the week 7. So in this week, we'll deal with the in lecture 32. We have learned about the installation and operation of drip irrigation system. So we know that drip irrigation system generally installed in two parts. First, we are installing the head control unit, and second is water distribution network. So head control unit is that contains of pumps that draw water from the source, either it is surface water or groundwater. Then various kind of valves like non-return valve, ball valve, flow control valve, and also we have fertigation equipment and filtration unit, right? So we have seen installation of each component in head control unit, and in water distribution network. Once we have installed head control unit, then in next line we have the main line. We need to connect this system with the main line, and in main line we have various submain line, right? Depending on the field shape, and in submain lines we are laying the laterals. Okay, on each laterals we have the what drip emitters, right? I hope I'm audible. Hello, hello. So let's continue our session. Next, in lecture 33, we have learned about the maintenance of various drip irrigation system components, right? So in that we have started with the maintenance of system. So we have seen various kind of filters, that is hydrocyclone filter that is worked on the based on central filter, it's also known as the media filter. In that we have the various grade of sands, right? That generally filtered out the poor irrigation water quality. And we have also seen the screen filter, right? In that we have the mesh, different kind of mesh that is available in this filter. So this is generally relate more like we are also using this kind of filter to filter water in our house, right? So it is basically contain of mesh. That mesh is having different size. Okay, so this mesh opening we are selecting based on our known irrigation water quality. Filter is the heart of the drip system, right? So if it got failed, right? So what due to that what happened? Entire system will get clogged, and that cause the heat difference, right? So we cannot reach it out the we cannot operate drip system at its full capacity what we have designed for. So we have also seen the maintenance of fertigation equipment, And in this fertigation equipment, we have done, seen in previous slide also. We have shown three equipment. One is the venturi injector, fertilizer tank, and injection system, right? And among that, generally we are using with drip, that is venturi injector, right? And that is work based on Bernoulli's principle. So the venturi injector, we are it should be operated with clean water for 10 to 15 minutes to prevent clogging, right? Before we start our irrigation via drip irrigation system, we need to operate with 10 to 15 minutes, right? Before we started irrigation. We have also shown the maintenance of main and submain lines. So in main submain lines, we have various kind of valves like flush valve, ball valve. So flush valve is available at the end of the submain pipes or lateral pipes. Okay. And ball valve is available at head end of the submain pipe. So it is generally used for control of the water flow. And in this kind of system, what we are using chemical treatment. And most commonly used chemical is that is hydrochloric acid and chlorine to remove the clogging and plugging, right? That is available in that main and submain line. And next to that, final component of drip irrigation system is drip emitter, that is laid on laterals. Okay, so lateral pipes as well as drip emitter. That also we have shown in lecture 34. We have started. We have shown the field demonstration of drip irrigation components. So again, as we discussed earlier, drip irrigation system generally divided in two parts. One is the control head, second is the distribution network. So in this figure, we can see this part, we can say this as the control head, right? So starting with this is the canal network that is available nearby our field. So we draw water from this water source to our farm pond, right? That is available in our field. So we are storing water in this, and we are diverting this water to field. Before that, we are doing certain operation, right? Based on our requirement. So the fundamental requirement is we need to filter out water, right? The available physical, chemical, and biological components in irrigation system, we need to filter it out, because the drip irrigation system we are dealing with that contain the drip emitters at individual plants, and that emitter is very small, right? That opening of that drip emitter is very small in diameter. So if our water contain any kind of impurity, that is directly affect the clogging of this drip emitter. So due to that, plants get not get the essential amount of water, and ultimately we are end up with losing our crop yield. So for that, we have the different kind of filters we have already discussed in last lecture. So filters like hydrocyclone filter, screen filter, media filter, based on requirement. And after, once we have done the filtration, so generally the screen filter is we are putting after the filtration system, right? We have first we have first we remove the larger impurities by hydrocyclone filter. Then that filter out filtered water we have injected. We have what we'll do, we'll inject the fertilizer in that water, right? So we'll allow sometimes in this system. It design is like that, so it will get mixed properly. And after that, what will happen, because we are injecting the chemicals, right? So that chemicals may react with the water that we are taking from this source, right? And that water that water will form precipitate of that particular chemicals, because we don't know the water that is coming, the quality of water which is coming every time. So due to that, that may form the precipitate by some chemical reactions. So that remove this precipitate, we are installing screen filter, right? That uh, so that will remove this kind of substance that is created. After that, we have the non-return valve, right, to restrict the backflow of water from this main line and submain line. So once we have designed this head, head control unit, we move on to the this main system, submain system, laterals and drip emitters, right? So we have seen that component also, and at what pressure, which and diameters of each pipes is we need to select, right, based on the discharge requirement. Then the we need also need to evaluate the drip emitters, right? So for evaluation of drip emitters, we have shown the various characteristics starting with the manufacturing characteristics, operational characteristics, and hydraulic characteristics. So manufacturing characteristics, generally we are dealing with the coefficient of variance, and that is at pressure 1 kg per centimeter square. While operational characteristic, we are deriving various emission uniformity, means how uniformly water gets distributed. That we will discuss also in upcoming slides during problems. And hydraulic characteristics, that is that is defined by this x, that is emitter exponent. And next to that, in week 7, we have also discussed the soil water movement and the drip emitter. As I discussed earlier also, that movement of the traditional water system and drip irrigation, micro irrigation system, that is totally different, because fundamental difference is the water movement. Kind of what in traditional irrigation system, we are ponding the soil surface, right? And we are injecting water at a huge amount. While in case of micro irrigation system, we are adding water at very slow rate, but too frequently. So that will create different pattern that we have understand uh, in this lecture, right? So also generally the physical process in the water movement in drip irrigation system is essentially a three-dimensional saturated unsaturated flow problem, right? Because when we are start applying when we'll start applying water, at that time soil is unsaturated, and it will starting saturating the soil surface, right? First it will the pattern is like this onion shape, right? So after sometimes the soil gets saturated, and the soil water movement will start in each direction, right, in horizontal as well as vertical direction. While in case of traditional irrigation system, we are only considering the vertical flow, right, because we are providing water to the entire field, right, entire field ponding, and so water only will go down only, right? But in case of drip irrigation system, as surrounding soil is dry, so water will also start moving horizontal, that we have also understand. Then the fundamental requirement of the soil water, to understand the soil water movement and the any kind of irrigation system, we need to understand the soil water characteristic curve. That curve is between volumetric water content and metric potential, soil metric potential. So this relationship we have also seen, and the hysteresis effect we have understand. So next to that, we we found that the soil properties basically that is available in our field and rate of water application that generally define the shape of this saturated surface, right? And the flow regime is 2 or 3 dimensional rather than vertical only, as I already discussed. The water is added at a high frequency, right? Because we are applying water too frequently, and soil water content is maintained with relatively narrow range. We are not provide irrigation to entire field. We are only dealing with the plant that plant roots, right? We are only targeting the plant roots. And next to that, we have seen various kind of uh, equations that is we generally required for the drip emitters. That is steady state solution for point source, steady state solution for surface ponding, steady state solution for line source emitters, and transient solutions. And we have also gone through two fundamental equations that is define the soil water movement in and the soil, right, in unsaturated zone or saturated zone. So basically, one of the famous equation that is Richard's equation that describes the water movement in unsaturated soil by combining Darcy's law and continuity equation, right? And it accounts both saturated and unsaturated flow. So Darcy's law that is generally dealing with the saturated flow, right? And Darcy's law states that the water movement in a soil is directly proportional to the hydraulic conductivity and hydraulic gradient, right? And here, which hydraulic conductivity is that? Saturated hydraulic conductivity, because we are Darcy's law is dealing with saturated hydraulic conductivity. Then the here what is H? That is potential energy available to move water through the soil, right? And that is given by metric potential plus gravitational potential, right? So Darcy's law also can be written for unsaturated flow, but in that case, here the value of such hydraulic conductivity is that it is for hydraulic conductivity at particular moisture content, right? So then we have combined each this principle with the continuity equation. So continuity equation that states the conservation of mass in the soil water system, and it states that rate of change of water movement, rate of change of water content in the soil element must be equal to divergence of water flux through element, right? That is delta Q, and that is given by Darcy's law, right? Because it defines the soil water movement. So let's uh, e- equate this equation. So when what continuity equation state that the change in moisture content is equal to divergence of the water flux through element. So del theta by del t is equal to minus del q. And what is q? According to that Darcy's equation, that is k theta del h by del z, right? And here del is, so let's put this h, right? Metric potential plus gravitational potential here, and the final equation of Richard equation can be written as this, that is del theta by del t, that is change in soil moisture content, is equal to del by del z in bracket unsaturated hydraulic conductivity in bracket del h by del z. This is del h by del z is what is hydraulic gradient, right? Because how water will move? Suppose we have water level like this, okay? So suppose this is the surface, water surface, okay? And we are providing water here, okay? And what will happen? This water will move vertical also and also horizontally. Why? Because the water will move from higher level to lower level, right? So that is due to basically hydraulic gradient, the gradient that is available on the soil surface as well as the water level we are targeting. In lecture 36, we have learned about the design and development of drip emitter. In that, this drip emitter design we have will show in this lecture. And we know that drip emitter is generally have three components: inlet, energy dissipator, and outlet. So this base component or inlet bar, that is inlet component. Then water will go into the Lambert button, and in that water will move in the zigzag path that will generally dissipate the energy of the water, and finally it will move through the cap, okay, or outlet section and form in form of droplets. So next to that, we have seen the design step in SolidWorks and 3D printing. So first component of the design is ideation, right? First, we need to create. We need to do creative processing for generating, developing, and communicating new ideas. Next to that, that ideas we need to process of planning and creation of project. And third one, what we are doing, we are process to predicting the performance of digital prototype. Means based on this design requirement, we'll design prototype and predicting the performance of this prototype. Once we have this efficient performance, we have found efficient performance of this prototype, we'll do the 3D printing, making three-dimensional solid objects from digital files, right? And finally, what we have created that will test, okay, using various kind of field and laboratory investigation. Then we have also understand the importance of single component drip emitter and two component drip emitter. So if you have any question till now, you can ask. Else we'll move on to the question answer session. Okay, let's start our question answer session. Okay, so let's continue our question answer session. So first we'll begin with the multiple choice question. First question is, in micro irrigation, drip emitters usually made up of, what's the answer? Answer is polypropylene, right? Why? Because we know that main line that is made up of HDP, that is high density polyethylene or polyvinyl chloride, and diameter of main line is 50 to 110 mm, and it should withstand the pressure head that is range of 4 to 6 kg per centimeter square. In case of submain pipe, It is made up of, again, same material, ATP or PVC, but the diameter of submain pipe is lesser compared to main line. And also the pressure capacity that can withstand, that is 2 to 5 kg per centimeter square. We have also, let's see the various component, that is ball valve. We know that it regulates the pressure in submain line. Flush valve, it provided at the end of the submain line to flush the impurity deposited at pipeline. While laterals consisted of low density polyethylene or low density of uh, polyethylene. And the diameter of laterals is 12 to 16 mm, right? And it should withstand the pressure of 2.5 kg per centimeter square. While we know that on laterals we have the drip emitters, that is emission device, also known as the drippers, right? And it consists of polypropylene. It is the very small device, right, of varying flow rates. We know that various kind of drip emitter flow emitter available, that is 2, 4, 6, 8, and 12. Also, more than this available, based on requirement, we can design, right? Question number 2, that is the process of gradually weighting of initial dry soil, that is known as option A, desorption, B, sorption, C, hysteresis, or D, drying, right? So we know that desorption is opposite of sorption, where we are that soil is released to water from soil particles and it leading to drying. But here what they are gradually waiting. So that process is known as sorption. And in that process, water is gradually absorbed on the soil surface and absorbed into the soil matrix, leading to the wetting of dry soil. Stresses, we know that the soil moisture content at drying and wetting phase is a different, right? That is known as the hysteresis effect. And drying, we know that this is simply removal of water from the soil. So correct answer is option B, that is option. Question number 3, according to American Society of Agriculture Engineering, is a recommendation, the pressure difference between inlet and outlet end of the hydrocyclone and sand filter should not exceed. The answer is 70 kilopascal, right? So according to the American Society of Agriculture Engineering, recommendation pressure between inlet and outlet of hydrocyclone or sand filters, right, should not exceed 70 kilopascal. So that is inlet and outlet of hydrocyclone as well as sand filter, both, right? Same question is asked here. So that should not exceed 70 kilopascal. And if it exceeds 70 kilopascal, what will happen? This pressure drop is important factor in determining when backwashing or cleaning of filter is necessary. So when pressure drop reaches 70 kilopascal, means the pressure difference is above 70 kilopascal. It indicates that filter is clogged with particles and debris, that generally relating to the reducing of the efficiency of filtration system. At this point, we must backwash the filtration system to restore the filter's functionality and ensure proper irrigation system. Maintaining of the pressure drop within recommended limits helps to ensure efficient filtering, prevent clogging of the irrigation emitters, and also ensure the optional performance of drip's irrigation system. Right. Let's move on to the next question. Question number 4. From the following components of a drip emitter, identify which one is not a drip emitter component. So option A given is the base, B is the cap, C is the Lambert path button, and D is the nozzle. Right. So we know that drip emitters typically consist of several key components designed to regulate flow of water at a very low rate. And base component is generally that is inlet, right? That is also known as bar. While cap is that is outlet section that serves to seal and secure the emitter, often helping to control the water flow and protect the internal mechanism. While Lambert button, we have seen last previous slide also during summary session. That Lambert part button that allows the zigzag water movement and generally that dissipate the energy. However, we cannot see the nozzle right in this drip emitter. Nozzle is available on lateral, right? On lateral we have the drip emitter. So, but drip emitter not contain any nozzle and it is not component of drip irrigation system. However, we can found nozzles in sprinkler system, right? And nozzle are used to disperse the water in a spray pattern at a higher pressure. That we'll also discuss in upcoming lectures, where we'll discuss about the sprinkler irrigation system. So answer is D. Question number 5. A process of making three-dimensional solid object from a digital file is that is known as simulation, molding, 3D printing, and decoding. So let's understand each option. Simulation. What is simulation? That is process of creating virtual mode of real system. Means we are simulating the various scenarios, real world scenarios to analyze the behavior of emitter, right? While molding is, it refers to the shaping of material. Typically, that material is the plastic or metal using mold, which is a common manufacturing process, but it is not directly related to the creating of objects from digital files like 3D printing. And 3D printing generally involves in making the three-dimensional solid object. We have discussed in last lecture of week 7. And decoding, that refers to translating or converting code data into the readable or understandable form. That is decoding. So which option is correct here? That is 3D printing that we are using to make a three-dimensional solid object. And we have used this system for the design of drip emitter. So answer is C. Next question, question number 6. To change the direction of flow in the 90-degree or 45-degree, the type of required pipe fitting is, so we know that to change the direction of flow, either it is 90-degree or 45-degree, we are generally using elbow, right? This is 90-degree elbow shown here, and there are various type of elbow. That is T connector, straight connector, straight connector, right? Again, that is of different design. So option A, that is given as connector, reducer, coupler, and elbow, right? So elbow is the right answer. Let's see other option also where it is using. Connector, we are generally using to join the two lines of the pipe in a straight line, right? So this is the connector, straight connector, as you can see here. Option 4. Reducer, a fitting that reduce the pipe size from larger to smaller diameter, that you can also observe in our home, where we made up certain kind of arrangement. Then coupler, a fitting that connects two pipes together, right? So it is generally we are using to join two pipes, not to diverting water from one direction to other direction. While elbow, we are using to divert water at 90-degree or other 45-degree. So answer D is correct. Let's move on to the next question. Question number 7. Which of the following is correct order of the components in a fertigation fertigation system starting from the pump, right? So we know that in drip irrigation system, first component is a pump, right? And it is responsible for creating a necessary pressure to move water from the source water, right? Source water pump is generally involved, and from source water we are diverting water to the hydrocyclone filter, and that we are using to remove the large impurities, large particles, heavier particles such as sand, silt from the water by centrifugal force. Next to that, we have the media filter. What media filter will do? It filters the sand and other media that trap smaller particles, right? As compared to the particles that is dealing during hydrocyclone filter. So in media filter, that is relatively small particle, and in addition to that, it is also removing organic matter, algae, and finer sediments. After media filter, we have the fertilizer equipment that we have discussed. We have generally three types: wedge rejector, fertilizer tank, and injection system. And in that, we are mixing the fertilizers, that is either major or macronutrient, to our water that is filtered through hydrocyclone and media filter. And the filters before fertilizer equipment are essentially to prevent clogging of this equipment, right? And there is the arrangement like 90 degrees turns to ensure the adequate time for thorough mixing in fertilizer equipment. Next to fertilizer equipment, we have the screen filter. And I already discussed the importance of screen filter, because after the fertilizers have injected, the water flows through screen filter. And the screen filter is the last line of defense, right? It captures any remaining small particles that would cause clogging in the later parts of the system. As we are injecting fertilizer that may form precipitate based on the chemical properties that fertilizer as well as the water incoming water quality. So that will also deal by screen filter. Then this water will move to the main pipe, right? So let's explore the option. Option A given is fertilizer equipment. Then we have media filter. No, we have the filter, media and hydrocyclone filter before fertilizer. So option A is wrong. We have pump, that is right. Then we have fertilizer equipment. No. After pump, we have the hydrocyclone filter, media filter, then fertilizer equipment, and after that we have the final defense line, that is screen filter, and that water we are generally diverting to the main line. And in between, we have the various valves that we also discussed. So option C is correct here. Okay. Next question. Question number 8. What is the recommended maintenance practices for hydrocyclone filter? So option A that is given, it should be backwashed for 5 minutes daily. Option B, it requires daily opening of the backwashing valve for cleaning the dirt inside the underflow chamber. Dirt inside the sand bed should be flushed through backwash valve. And final option, it needs to be backwashed weekly to remove accumulated debris. So we have shown that hydrocyclone filter, it should be installed before sand and screen filter. We have seen the previous slide also. And it requires the least maintenance as compared to other filters. While for cleaning the dirt inside the flow chamber, open the backwashing valve daily, right? So we need to open backwashing valve daily in case of hydrocyclone filter, and flush the chamber to remove the clogging materials. So, which option is correct here? We need to clean back flush every day. So, correct option is B. It requires daily opening of backwashing valve for cleaning the dirt. Question number 9. How frequently should the sand filter be backwashed during operation? So, this is the sand filter, right? So, we know that sand filter should be backwashed every day for 5 minutes to remove the silt and other dirt accumulated during the previous day's irrigation. Once in a week while a backwashing. So, this is the cleaning of filter, right? Once in a week, we need to backwash, and backwash water should be allowed to pass through the lid instead of backwash valves, right? The sand in a filter bed is a strip to the filter candles without damaging them. We have discussed almost all this, and this question we have also solved, right? That pressure difference should not exceed the 70 kilopascal. So which option is right here? Weekly while allowing backwash water pass through the lead. Yes. Then next question. Twice a day. No, this is not. This is wrong. Daily for 5 minutes to remove the silt that accumulated during irrigation. No, during irrigation, not it is the previous day irrigation. Okay. And when pressure drop exceed 100 kilopascal, back flush should be initiated. No, this is the 70 kilopascal, right? So option C is correct. Question number 10. What is the recommended practices for maintaining a screen filter during a drip irrigation system? So we know that screen filter flushing is scheduled daily interval is necessary to maintain the screen filter. So we have seen that in each filter we need to clean it daily before irrigation. It is recommended to flush screen filter if pressure drop more than 5 meter of a column or 0.5 kg per centimeter square. While in case of hydrocyclone and media filter, sand filter, it is 70 kilopascal. Before start of drip irrigation system, the flush valve on the filter lid should kept open so that dirt and silt is flushed out. Okay. So we need to open the flush valve on the filter lid, as you can see here, to remove the dirt and silt. And filter element is taken out from the filter that we need to follow in each one general procedure. So which option is correct here? Backwash the filter weekly to remove the dirt and sand particles. No, need to do backwash daily flushing. Open the flush valve on the filter lid before starting the irrigation system to remove the accumulated dirt and silt. Option C, monitor pressure drop, and if it exceeds 0.5 kg per centimeter square, plus the filter. Yeah, option C is right here. Next question. Why is it important to operate Venturi injector with clean water for 10 to 15 minutes before and after irrigation? So before and after irrigation, Venturi injector should be operated for 10 to 15 minutes. We know that we have learned, but they are asking the reason. Why so? Option A, to increase the suction capacity of the Venturi injector, to ensure the removal of the leftover fertilizer that could clog the suction port of the Venturi injector, to reduce the pressure in the irrigation system before applying fertilizer, to balance the pH level in the Venturi injector. So option B, right? Why injecting water, clean water for 10 to 15 minutes before and after irrigation, we are ensuring that it will remove the leftover fertilizer that may generate the problem of clogging, because running water may not create any problem, but once we stop our irrigation, what will happen? The water will get stagnant, and whatever we have mixed in fertigation system, that after some time that there is a chance that may form the precipitate, right? And the clogs that may create the problem of clogging in drip image. Question number 12. During chlorine treatment in drip irrigation system, why does the efficiency of chlorine injection depend on the pH of water? So we know that clogging or plugging of a drip emitter or orifice of a bivalve is due to the precipitation and accumulation of the certain dissolved salt like carbonate, bicarbonates, iron, aluminum, iron, calcium, manganese salts, right? Depending the source water quality. The clogging is also due to the presence of microorganisms, that is biological component, and the related to the iron and sulfur slimes due to the algae bacteria. Now, the efficiency of chlorine injection depends on the pH of the water, because chlorine is a less sensitive in a water with a high pH. It cannot do the properly filtration at a higher pH. Therefore, a higher pH level requires a more chlorine, and that ultimately ends up with a higher cost for a particular farm. This ensures that microorganisms like algae and bacteria are properly controlled in the system. So, at higher pH, we need to inject higher chlorine, right, to remove the bacteria and algae. So, chlorine reacts more effectively at higher pH. No, this is wrong. Presence of algae and bacteria reduces when pH level is high. No. Higher pH requires more chlorine to achieve the same residual chlorine level due to the decreased effectiveness. Option C is right. Right. At higher pH, the effectiveness of chlorine what we are adding that is less. Due to that, we need to add more chlorine to increase its effectiveness. Option C is correct. Let's also explore the other treatment, that is acid treatment and chlorine treatment. So in acid treatment, we are generally using hydrochloric acid or sulfuric acid. It is injected into the micro irrigation system at a rate suggested in a water analysis report. And acid treatment is performed till the pH of 4 is observed at the end of 5. After achieving the pH of 4, system is shut off for 24 hours, and next day system is flushed by opening the flush valve and lateral network for irrigation. While in case of chlorine treatment in the form of bleaching powder is performed to inhibit the growth of microorganisms like algae and bacteria. Bleaching powder is dissolved in the water and the solution is injected into the system about 30 minutes. So whatever solution we have prepared from bleaching powder, we are allowing that for 30 minutes. And then system is set up for 24 hours. Again, you perform same similar operation. The recommended chlorine dosage is generally 0.5 to 1 ppm concentration is applied continuously in continuous form, or 20 ppm for 20 minutes at the end of each irrigation cycle. For algae and for slime, 1 ppm free residual chlorine is maintained at the end of each lattice. So there are 3 scenarios here. Either we can continuously allow the chlorine. So we need, in that case, the chlorine concentration is 0.5 to 1 ppm. While in second case, that is 20 ppm. In that case, we only allowed to do for 20 minutes. 20 ppm for 20 minutes. And that is also at the end of each irrigation cycle for algae removal, right? So this 20 ppm is for algae removal. While for slimes, we are injecting 1 ppm free chlorine residual at end of each lateral, right? So next question, question number 13. During chlorine treatment in a drip irrigation system, why does the efficiency of chlorine injection depends on the pH of water? So I think this question we have already discussed, right? Because at a higher pH, it requires more chlorine to achieve the same residual chlorine level due to the decreased effectiveness. Option C is correct. Question number 14. What is the main reason for difference between drying and wetting curves in the soil water characteristics curve? So we know that why this is happening. Let's understand. So soil water characteristics curve has a different for drying as well as wetting condition, and that phenomena is due to the capillary hysteresis effect. Okay. So in drying curve, also known as the desorption, when soil is initially saturated and will start extracting water from that, right? What will happen? How will extracting this water by applying the suction? Okay, we are sucking the water from soil, and the water content due to that, what will happen? Water content of the soil will gradually decrease. So this graph is this, and this process is known as desorption. While when we are applying water to the dry soil, it will start again gaining the soil moisture content. So soil moisture gets increased, and but the path that is followed, that is waiting path, follows during sorption is different, and this is basically due to the capillary hysteresis, right? And it occurs because of a soil water retention, release of release follow different pathways due to the factors like. So this difference is basically governed by the pore size distribution of the soil. Means soil size, right? What kind of pore it have, then air entrapment, air entrapment property of that soil, and way water moves in and out in the soils, means the rate of water we are injecting. So our answer is capillary stress is caused by different pathways of water movement. Correct answer is D. Okay, so let's take a break here. Do you have any question? So we have seen. Hello, am I audible?
Yes, sir.
Okay, I hope you got the answers what you have sought. Do you have any question?
Not now, sir. I'm clear till this.
Perfect. So let's take a break here of 5 10 minutes. We'll join. Okay. Okay. So, Okay, so am I audible? I hope I'm audible. So let's resume our session. Okay. Uh, so in match type of question, so question number one, in the following match each of the entries in a group A with the most appropriate link entry in the group B. So option A, that is given ball valve. We know that ball valve is used to control the water flow and it is connected at the inlet end of the sub main, right? Means at side of inlet. Then flush valve, that is again why we are using flush valve, we are using to clean the sub main line by allowing accumulated debris and impurities to be flushed out, making it ideal to be placed at outlet end. Okay, so option B, connected at the outlet end of the sub main uh, flush valve. While call valve we are using for it is connected at inlet end of the submain. Government takeoff, that is also known as a GTU. It is connected to joint submain with the lateral pipe, right? So option one, connected to the joint sub connected to the joint submain with lateral pipe. So that for that we are using GTU. Fertilizer injection unit, that is connected between sand and screen filter, right? And above that, it may be also hydrocyclone filter. It is connected between hydrocyclone, sand, then we have fertilization unit, and finally we have screen filter. We have this discussed detail also, right? So option two, connected between sand and screen filter, and end cap is connected at the outlet end of the laterals, right? That is to restrict the flow outside of the lateral. So correct answer is this. Question number two. Again, we need to match the group A component with the most appropriate answer that is related to the group A. So first is the idea maker, right? So idea maker is 3D printing software that generates the .g code files for controlling 3D printers, right? So that is more related with option 4, G code file idea maker. Flow inside drip emitter. In that, generally we are dealing with the conservation of mass as well as momentum equation. We know that the flow inside drip emitter is analyzed using conservation principle like mass and momentum to understand the hydraulic performance of water as well as drip emitters. Then we have the solid work. For that, what we are using? CAD software, right? CAD software, SolidWorks, and that create the file that is saved with .stl. So option A is correct here. Then we have the test bench. The test bench where we are using for evaluation of hydraulic emitter. And final, that is in Ditnet and TET. So it is more related with the Lambert button, and Lambert button is a part of energy dissipation component of drip emitter, right? And its structure often relates to the Lambert structure in drip emitters, which influence the water flow regulation. Means energy dissipation. So this is the correct answer. Question number 3. Match the components of drip irrigation system that is given in group A with their function specifications. So option 1 that is given as main and submain line. Right. So we know that main and submain lines installed underground to protect from damage by farm equipments like tractors or any machines that we are using during crop cultivation. And the installation depth of main and submain lines varies from 45 centimeter to 60 centimeter, and that is depends on the diameter of the pipes, right? So for 45 centimeter, 45 for the diameter of 1.2 to 6 centimeter pipes, we are installing that on 45 centimeter. For 6 to 10 centimeter pipes, we are installing at 60 centimeter, and 75 centimeter depth, we are generally installing the pipe that is diameter over 10 centimeter, right? So 3 depth, 45 centimeter, then 60, and then 75. So this is in ratio of 15, increasing interval of 15. So the 45, the diameter is 1.226, and 60 centimeter, 6 to 10 centimeter diameter, and 75 at 75 centimeter depth means 0.75 meter depth. The diameter of pipe is if it is above 10 centimeter. So which option is correct here? Installed underground at a depth 45 to 75 centimeter based on pipe diameter or pipe size. Option A is correct. And laterals, we know these pipes that distribute the water, right, uniformly in the rows. And in laterals, we have the drip emitter. So installed based on crop requirement, can be on grounded or underground, right? So this is the answer. Then ball valve, we know the ball valve that controls the water flow, right? And it positioned at the inlet end of the submain system. And flush valve, also we are using in submain, but it is at the end of submain, right? To facilitating the system flushing to remove the particles that may gather, right, with the poor irrigation water quality. We are flushing to improve the system efficiency. Installation of, let's also explore other important information that we have already saw in our previous slide, right? So, except for a fully portable system, both the mains and submains are installed underground at minimum depth of 0.5 meter, means 50 centimeter, such that they are unaffected by cultivation or movement of heavy harvesting machinery. And this category we have already discussed, and this is given by United States Soil Conservation Service, USSCS, right? Next question, so number 4. Again, the component of drip irrigation is given. We need to match with its function as well as specification. So first option is given as a main line. So let's solve this question. Before that, let's quickly recap what we have learned in the previous week. So all the components given is part of distribution network here, right? So in distribution network, it consists of pipes, various pipes and valves. Also on the laterals, we have an emission device to distribute the water to the crop. So these pipes generally we have categorized in three terms: main lines, sub-main lines, and laterals. Right. So main lines that is made up of that I'm again revising this content. So it is made up of high density polyethylene or polyvinyl chloride, but diameter of this pipe is 50 to 5 to 11 centimeter, and pressure it can withstand is up to 4 to 6 kg per centimeter square. While submain line, we have the less diameter that is 37 to 75 mm, and also it can withstand with lower pressure that is 2 to 5 kg per centimeter square. We have the ball valve also to regulate the water supply in the submain, and the flush valve at the end of submains to flush the impurity deposited in the pipeline. While in submains lines, we have connected it, the laterals is connected in the submain line. The water will flow from submains to laterals, and laterals made up of LDPE or LLDPE, and diameter of laterals is 1.2 to 1.6 centimeters. That is very small, and it should withstand the 2.5 kg per centimeter square pressure. And on laterals, we have emission device that is maybe various kind of drip emitters, right? So and that is made up of polypropylene. Let's solve this question. Main line, we know that main line that consists of HDPE or PVC. The diameter is 5 to 11 centimeter, and it must withstand 4 to 6 kg per centimeter square pressure. Ball valve we are using to regulate the water supply in the pipeline. Laterals, why we are using laterals? So laterals that is connected with the submain lines, main line and submain. Submain is connected to the laterals, and laterals is made up of LDP or LLDP, and diameter of lateral is about 1.2 to 1.6 centimeter, and it should withstand 2.5 kg per centimeter square pressure. Next next option, emitters or drippers. We know on laterals we have the drippers that is made up of polypropylene. So it is a small device that emit the water made up of polypropylene used for micro irrigation system. And performance evaluation of emitters, it involves the attaching drippers at specific discharge rates, noting pressure at laterals and measuring collected water to evaluate efficiency under varying conditions. So this option is more to the performance evaluation of emitters. Generally, what we are doing in performance evaluation of emitters, we are in uh, do the experimentation on specific discharge rates, right? And noting pressure of laterals, and also collect the pressure at outlet. So at each pressure, what is the flow rate? Based on that, we'll also solve question numerical question based on this concept. Then you will get more idea. This we have already discussed. So okay, before moving on to the numeric type of question, do you have any question? Okay. So first question is 4-point source drip emitters are used to irrigate each mango plant grown at 7.5 by 5 meter spacing. Average operating pressure of drip emitter is 100 kilopascal, and the average discharge is 4.2 liter per hour. Exponent as X is given for drip emitter, that is 0.5, and manufacturer's coefficient of variation CB also given is 0.05. The desired emission uniformity is 85%. The minimum operating pressure of the drip emitter is in a kilopascal we need to identify, right? So we know that this emission uniformity is given by this formula, right? In 1 minus 1.27 into coefficient of variance divided by number of emitters into minimum discharge divided by average discharge. So NE is given, that is 4, right? We have the 4 point source emitters. So NE is a 4. Q average, that is given as 4.2 liter per hour. Coefficient of variance given is 0.05. P average is 100 kilopascal given here, right? And uniform efficiency is 85% for X of 0.5, right? So crop spacing is also given, that is 7.5 by 5 meter. We know that discharge is directly proportional to the pressure, but for different kind of emitters, we have the different emitter exponent. And uniformity, emission uniformity is given by this formula. So let's put all this given value in this, and let's identify the pressure, right? Minimum pressure required for drip emitter to achieve the 85% in uniform efficiency, emission uniformity. So Q mean by Q average is equal to EU by 100 into this component, right? So EU is given is 85, 100, 1 minus CV is 0.05 and number of emitter is 4. So the ratio of Q minimum by Q average given as, we found that is 0.8778. Now from equation 1, we can write that Q minimum is directly proportional to P minimum raised to X, and Q average is direct is equal to P average raised to X. So this ratio we have Q minimum by P minimum, right? That we have identified from this equation, and X is also given. So the ratio we obtained is 0.77, and we know the P average is 100. So P minimum is 77 kilopascal. Now question number 2. The performance test was conducted for 10 numbers of randomly selected drip emitters for 8 liter per hour discharge using standard hydraulic test bench. The following observation of drip discharge were collected from test sample. So this is the discharge for 10 numbers of observation. We need to identify the manufacturer's coefficient of variation for drip emitter. Okay, sorry, that is given already as a 0.048, right? We need to identify emission uniformity. So we have shown the formula of emission uniformity, that is given by this, and here CV is the coefficient of variance that is given as 0.048. Number of emitters given, right? 10 number. Q minimum that will compute from this, and average emitter discharge that will also calculate from this. So Q average is equal to sum of all this divided by 10. Q minimum is here. So Q minimum is 7.4, first one only, right? So let's put all this given in this equation, and uniform efficient emission uniformity we are obtaining, that is 92.68%. Next question, question number 3. An irrigation system has a supply flow rate QS of 150 liter per minute. The desired concentration of chlorine in the irrigation water U is given as 2 ppm. Right, this is U. Sorry for mistake. So, right, this is U. That is given as 2 ppm. And the concentration of chlorine in the solution to be injected C is 10%. Calculate the rate of injection, that is QC, of the chlorine solution into the system. So let's write the given here. So QS, that is irrigation system supply flow, QS given, right? So irrigation supply flow, that is 150 liter per minute. U is desired concentration of chlorine in the irrigation water, that is 2 ppm we required in this upcoming flow rate. And the concentration of chlorine in the solution to be injected C measured was 10%. So we know that to calculate the rate of injection of QC to achieve the 10% concentration, right, of 2 ppm. At what rate we need to inject? That is given by this formula, right? So QC injection rate is equal to the whatever concentration we are desiring, that is 2 ppm here. We what the desired concentration of chlorine in irrigation water, that is 2 ppm, means 2 milligram per liter water we want in irrigation water, and irrigation flow rate is for 150 liter per minute, right? And what is the concentration of chlorine in the solution to be injected? That is 10%. So divided by 10. So liter is on. What we have here? 2 milligram into 150 minute. Right? Multiply divided by 10. And in addition to this is the part of formula. Right? So after that, all unit conversion, we need to convert this minute into hour. So we know that 1 hour is equal to 3 minutes. So let's convert all this here and we'll obtain QCS injection rate of chlorine as 0.18 liter per hour. So let's move on to the next question, question number 4. An irrigation system using drip emitters has the following record flow rates for 8 emitters in a liter per hour. So emitter 1 given as 3.8 liter per hour, 2, 3.6, 3.5, 4, 3.9, 3.7, 4.1, and 3.4 liter per hour. And what we need to compute here? Given the nominal flow rate QR, that is given as 4 liter per hour, and compute the following operational characteristics. All the equations are given here. First, we need to calculate the emission uniformity using this formula. Here we know that uniformity coefficient is given by Qn by Qa multiplied by 100. So what is Qn here? That is the average of lowest 1/4 emitter flow rate, and Qa is the average flow rate. So average of 1/4 emitter means here we have total 8 emitters, right? And 1/4 of average of 1/4. So 1/4 emitter is equal to, we have only 2 here. So lower average of lower 2 emitters, right? So we need to identify two lower emitter discharge from this and need to average that. Divided by average of each, right? So next question, we need to identify absolute emission uniformity, and that is given by 1/2 in bracket Qn by Qa plus Qa by Qt, right, into 100. Here Qn is the same what we have observed, we have estimated here. Average of lowest 1/4 emitter. Qa is the average of each emitter, and Qt is average of highest 1/8 of the emitter flow rate. Here highest, right? And Qn is the average of lowest 1/4 emitter, while Qt is the highest of 1/8 emitter, means highest observation we need to record, because 1/8. Here we have to total 8 emitter. So 8 will go gone. We have select highest observation as a Qt. Need to put all this in this equation to obtain result. And in last, we need to identify the percentage difference, QD, and that is given by QR minus QA divided by QR. So nominal flow rate given is 4 liter per hour, and QA will observe from this average share, and that will identify the percentage difference. So you can identify, you can try to solve this question. Let's take, I'm giving 2-3 minutes here to you. Okay. So after that, I will solve this. Okay, so I hope you tried this solution and try to solve this question. Let's solve again here. So first we need to identify emission uniformity. So first that is given by, we know that Qn by Qa multiply by 100. So what is Qn? Qn is the average of lowest one-fourth emitter flow rates. So identified one-fourth emitters we have complete, that is lowest of two. So this average is lowest of one-fourth emitter flow rates, average is 3.45 liter per hour, while average of all emitter, that is 3.75. So 3.45 divided by 3.75. So EU is equal to 92%. Next, absolute emission uniformity. In addition to the Qn, we also need to identify Qt. So that is the average of highest one eight of the emitter flow rates. So here we have total 8 emitter, and from that one eighth of the 8 is 1. So we need to select one emitter highest flow rate, and let's put in this equation, that is Qn divided by Qa plus Qa divided by Qt, bracket 1 half multiplied by 100. So answer is 91.5%. Now third quantity that we need to identify, that is percentage difference. That is given by QR minus QA. So QR is given as nominal flow rate, that is 4. 4 minus average is 3.75 divided by 4. So that is 6.25%. So in this example, what you have learned? Emission uniformity is 92%. Absolute emission uniformity is 91.5%, and percentage discharge QB is 6.25%. And this result help to determine how consistently water applied across the different emitters and whether system meets irrigation uniformity standards or not. Right. Okay, next question. Question number 5. In the drip irrigation system, the performance of emitters is evaluated based on three characteristics. We know that it is manufacturing characteristics, operational characteristics, and hydraulic characteristics. Here, manufacturing characteristics, we know that we are dealing with coefficient of variance. CV is used to assess the manufacturing quality of emitters. If the standard deviation of the discharge rate is 0.2 liter per hour and mean discharge is 4 liter per hour, then we need to calculate CV for the emitters. Next, operational characteristics, that it assumes that emitter discharge flow rate varies due to the system pressure in operational. While if the reference discharge rate is 4 liter per hour at 1 bar, calculate the discharge rate when pressure is 1.5 bar. Given the emitter flow exponent is 0.5. And the third quantity and hydraulic characteristics, we know that the discharge rate of emitter is dependent on the pressure, right? And if the emitter discharge rate is again 4 liter per hour at 1 bar, and the pressure loss due to the friction is given as 20%, in that case also we need to calculate the new discharge rate for the emitter. So let's try to solve this question. So question 1, first quantity we need to identify, that is coefficient of variance. And we know that coefficient of variance is given by standard deviation of discharge divided by mean discharge. So both quantities given here. So standard deviation is 0.2 liter per hour and average is 4 liter per hour. So what is the coefficient of variance here? It is 5% or 0.05, right? So based on this ASAE interpretation of coefficient of variation for manufacturer, that is, if it is below 0.05, right, in both line as well as point source emitter, that is excellent. Here is excellent. So next to that, operational characteristics, that emitter discharge with changing pressure. We know that this relationship, right? Operational characteristic relationship, that flow rate is directly proportional to the pressure, right? So pressure raised to x. So here x is emitter exponent, and that varies for different kind of pressure, right? It is point source, non-point source, types of flow path in that emitter. So here given is Q1 is given here 4 liter per hour. Pressure is a 1 bar, right? And P2 is given as 1.5 bar. Exponent is also given 0.5, and at that time we need to identify Q2. So simply we will put all these given quantities in this equation and we'll obtain Q2 as 4.9 liter per hour. Next, last quantity in hydraulic characteristics, discharge with pressure loss due to the friction, right? Hydraulic characteristics, that is generally dealing with the pipe material based on the characteristic of surface of this pipe. While operational characteristics, that is emitter discharge with changing pressure of the system, right? And here it is the pressure lost due to the friction, because we are dealing with the hydraulic characteristics. In that case, what we need to do, we need to identify the, if the emitter discharge given as 4 liter per hour at 1 bar, pressure loss due to the friction is 20%. Calculate the new discharge rate for emitter, right? So let's solve this question here. We know that pressure drop is given as 20%, right? So simply what will happen? Our previous pressure is P1 is 1 bar, right? 1 bar. And new pressure, what will be happen? So due to the friction loss, the pressure get reduced by 20%. Simply we'll do 1 minus 0.2, that is 0.8 bar. Right here, right? It's already calculated. Now calculate the new discharge rate using the same pressure equation. What we have seen previously, right? Q1 divided by Q new here is equal to P1 divided by P new raised to x, and x is given as 0.5. So what is our new discharge? That is 3.576 liter per hour. And this is the characteristics of the flow regime, right? This is the flow regime of the emitter and value of emitter exponent. Based on that, we have classified the types of emitter. So for, if the value of exponent is between 0 to 0.3, means it is the pressure compensating type emitter. It means if you see this relationship, Q is equal to K P raised to X, right? So here, see, if X is, our X is lower here, suppose 0, right? It means this component is totally 0. Means discharge is not related with the pressure, or it is minimally controlled by pressure variation. So in case of pressure compensating tape emitter, we have learned that it is, in that case we are obtaining constant pressure, right? Even we have the pressure variation in our system. As we have, as the exponent value get increased, the relation between this Q and pressure is also become stronger. So in case of capillary and microtube type of emitter, there is a higher correlation between pressure and discharge. So as pressure gets varies in the system, that will directly affect the discharge, right? So I think we are uh, at the end and we have very limited time. So we'll solve this question in next uh, upcoming session. So before we'll end up this session, if you have any query, you can ask directly. Right now we have 5 minutes. So do you have any question, anyone?
No.
Okay. So let's quickly summarize this session. Like what we have done in this session, we have solved various questions related to the installation, operation, and maintenance of drip irrigation system and its components. Also, we have solved Richard's and uh, Richard's equation. Right, we understand its importance in the soil water movement during irrigation supply, particularly with emitter. So, and also last lecture uh, of the this week, we have saw the design of drip emitter using SolidWorks kind of software. So I think is the end of the session. If you don't have any question, uh, I'm stopping this session here. Also, if you have any question, you can directly write to the provided email ID. So I hope you have enjoyed this session. So thank you so much for joining. Thank you.